Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. In their quest to understand the first stars and galaxies that lit up the cosmos, astronomers are still in the dark but getting closer to enlightenment, one discovery at a time. That's the incredible, inescapable conclusion from unprecedented discoveries by the James Webb Space Telescope, JWST, the $10 billion time machine that just officially closed its first year of observations. Designed to glimpse the faint infrared glow of the universe's earliest luminous objects, JWST's vision reached back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. But its haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy prediction, with dozens found so far, and that makes scientists freak out. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this." In the weeks and months following JWST findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalous, big, and bright early galaxies be due to flaws in analyses of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or, just maybe, were they the first hints that the universe is more strange and complex than even our boldest theories had ever supposed? And the Big Bang Theory, was it wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. To understand the dilemma, let's go back to when the universe was believed to have been formed. After the Big Bang, the infant universe began cooling off. Within a few million years, the roiling plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration, known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It has exerted a powerful influence over the cosmos, especially at first. In the standard picture, cold dark matter, a term that means invisible or slow-moving particles, was flung about the cosmos indiscriminately. In some areas, its distribution was denser, and in these regions, it began collapsing into clumps. Visible matter, meaning atoms, clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour, water, yeast, and raisins. When you combine these ingredients, the yeast begins respiring, and the loaf begins to rise. The raisins within it, standing in for galaxies, stretch further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter lambda. Plug values for cold dark matter, regular matter, and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, lambda CDM, model matches almost all observations of the cosmos. One way to test this picture is by looking at the very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to about 400 million years after the Big Bang. This was surprisingly early for a galaxy, but it did not cast doubt on the lambda CDM model, in part because the galaxy is tiny, with just 1% of the Milky Way's mass, and in part because it stood alone. Astronomers needed a more powerful telescope to see whether GNZ11 was an oddball or part of a larger population of puzzling early galaxies, which could help determine whether we are missing a crucial piece of the lambda CDM recipe. That's why the James Webb Space Telescope, JWST, was born. Renowned as the largest, most powerful observatory ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed. And that promise was kept as the first discoveries were obtained within just weeks after JWST's full operations. They were beyond astronomers' wildest dreams. It has seen galaxies breathtakingly close to the dawn of time, probed the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of worlds in our solar system. But it's just getting started. As Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built, at stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. JWST's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As JWST scientist Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm, but to break it. You just don't know how they will break it." Researchers use a version of the Doppler effect to gauge the distances of objects. This is similar to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, and so its light stretches to longer wavelengths and appears redder. The magnitude of this redshift is expressed as z, where a given value of z tells you how long an object's light must have traveled to reach us. One of the first papers on JWST data came from Naidu, the MIT astronomer, and his colleagues, whose search algorithm found a galaxy that seemed inexplicably bright and unaccountably distant. Naidu dubbed it glass Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed glass Z12. Other astronomers working on various sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CR7 Z1749, whose light appears to have left 13.7 billion years ago, just 220 million years after the Big Bang, barely an eye blink after the beginning of cosmic time itself. These putative detections suggested that the neat story known as lambda CDM might be incomplete. Somehow, galaxies grew huge right away in the early universe. You don't expect to see massive galaxies, said Chris Lovell, an astrophysicist at the University of Portsmouth in England. They haven't had time to form that many stars, and they hadn't merged together. In a study published in November, researchers found that JWST's early bright galaxies were significantly heavier than those predicted by computer simulations based on the lambda CDM model. While some claimed JWST was challenging cosmology, others noted the model's predictions aren't definitive due to the complex nature of visible matter and early cosmic events. The ages of some high redshift galaxies have been re-evaluated, with some being reassigned to later stages of cosmic evolution. For example, CR7, Z1749, initially thought to be extremely distant, may actually be part of a closer cluster, possibly obscured by dust. Naidu noted that CR7, Z1749 is an unusual galaxy, being very low mass and dusty, which is unexpected. Accurate distance measurements for such galaxies depend on JWST's advanced spectroscopic capabilities, which provide detailed information about a galaxy's history, unlike photometry, which only measures brightness. Naidu and others who found large early galaxies measured redshift using brightness-derived measurements, essentially looking at faces in the crowd using a really good camera. That method is far from airtight. At a January meeting of the American Astronomical Society, astronomers quipped that maybe half of the early galaxies observed with photometry alone will turn out to be intruders, dusty, dimmer galaxies that, when confirmed with spectroscopy, are in fact redshifted only a bit and billions of years younger. This healthy skepticism has led some scientists to question whether they are interpreting the data correctly. JWST scientists pointed out that data from a small fraction of the instrument's first observing cycle could not be definitive. Many astronomers caution that researchers have yet to complete the task of analyzing the full year of data JWST has obtained, and its precision observations mean that reassessing objects thought to be in the early universe will soon be routine. For instance, Hubble's GN-Z11 galaxy was confirmed at a redshift of 11.1 through JWST spectrometer. Detailed spectroscopy also enabled Lovell and colleagues to correct the distance of another galaxy, thought to be among the earliest yet detected. The study found the galaxy is not exceptionally distant, but rather about 12 billion years old, not 13.5 billion. Still, spectroscopic results are just coming in, and some will likely challenge current models. Webb's findings so far, however, suggest that cosmology's fundamental tenets are correct. The data from its first year of operations showing bright and large galaxies doesn't yet rewrite cosmic history, but could mean theorists have underestimated the universe's complexity. Researchers are revising their methods, such as better simulations, to explain rapid galaxy formation post-Big Bang. Consequently, JWST's detailed data